Good afternoon, children. So, in afternoon session, we are going to the important topic vertical oscillations of a spring. Okay. So, we are taking as a spring, which means massless spring with a stiffness constant or force constant K attached in a sailing. Let the length of the spring before a loading mass L, capital L. If the block of mass M is attached to the other end of the spring, then the spring elongates by a length small l. Let F1 be the restoring force due to stretching of spring. Due to mass M, the gravitational force acts vertically downward. We know that. So we can draw the free body diagram for this system. The system is under equilibrium. So F1 plus mg. But the spring elongates by small displacement L. Therefore, we can write as this F1 directly proportionality to L. So we can modify these equations of proportionality. So F1 equal to minus KL. Here minus K be the force constant. The minus value tells us it is always opposite direction to the displacement. And then substitute the equations 10.28 in the equations of 10.27. 10.27 is F1 plus mg equal to 0. We know that F1 equal to minus KL. So substitute the value of F1. So minus KL plus mg equal to 0. So mg becomes KL. So modify these equations m by k equal to L by g. Suppose the second case. Suppose we apply a very small external force on the mass such that mass further displaced downward y displacement, then it will be oscillate up and down. Now the restoring force due to the stretching of spring F2 directly proportional to y plus L. The same way we can write as F2 becomes minus ky and kl. So multiply the minus k in bracket inside of the bracket. Since the mass move up and down with the acceleration produces of d squared y by dt square, because the object will be moving up and down, so they are chosen as a y axis. So minus ky minus kl plus mg equal to md squared y by dt squared. After applying of the free body diagram, we get this equations 10.31. So the net force acting on the mass due to this stretching is F equal to minus ky minus kl plus kl equal to minus ky. So applying this Newton's law, we get mg squared y by dt squared equal to minus k square y. So d square y by dt square equal to minus k by m into 5. Finally, we have derived the equations of time period. So time period t equal to 2 pi root of m by k second. Already we are derived these equations. So put the value of or rewrite these equations by equation 10.29. So t equal to 2 pi into root of m by k. 2 pi root of m by k in equation 10.29 is tells us L by g. So replaces m by k as L by g. So these equations of 10.35 we are derived the equations g. So get the value of g from 10.35. And second topic, combinations of springs. The spring constant of four constants are called as a stiffness constant. It is measure of the stiffness of the spring. The larger value of the spring constant, stiffer is a spring. This implies that we need to apply more force to compress or elongate the spring. Similarly, a smaller value of the spring constant, the spring can be stretched or compressed with lesser force. So springs can be connected in two ways. Either the spring can be connected end to end and also series connections, or alternatively connected in parallel. The following observation. The first one, springs are connected in series. In second case, springs are connected in parallel. So first one we are going to see springs connected in the combinations of series. So when two or more springs are connected in the formations of series, we can replace all the springs in series whose net effect is same as in all the springs or in series connections. Given the value of individual spring constant K1, K2, K3, we can establish a mathematical relationship to find out an effective spring constant Ks. So let us consider only two springs whose spring constant are K1 and K2. Figure 10.17 tells us the connections of series. Let F be the applied force towards the right, since the spring constant for different spring are different in the connections points between them is not rigidly fixed. The string can be stretched of the indifferent lengths. Let x1 and x2 be the elongations of the spring from the equilibrium position due to the applied force. Then the net displacement of the mass point is x equal to x1 plus x2. So the spring resultant tells us minus k of x1 plus x2. So x1 plus x2 becomes minus of f by ks. The spring is in the combinations of series. So minus of k x1 equal to minus of k x2 x2 equal to f. From this equation we get the value of x1 and x2 separately. This is the effective spring constant can be calculated. Minus of f by k1 minus of f by k2 equal to minus of f by ks. So the resultant value 1 by k is equal to, because of the constant term of f, cancel to 1 by k is equal to 1 by k1 plus 1 by k2. So the common term of k is, taking the LCM, we get the equations of K is equal to K1 K2 by K1 plus K2. These equations of resultant value of series the spring constants K can be asked in one more questions. Okay, suppose we have two n springs connected. We have to connect it in n spring. The effective formula is 1 by k is like as 10.41. The similar way we can write as 1 by k is equal to n by k. So k is equal to k by n. So another method, it is the parallel combinations. Let's see the diagram. The two springs are more connected in the parallel. We can replace all the springs in the equal springs of whose net effect is the same for all the springs in parallel connection. So let the force F is applied towards same direction as right. In this case, both the springs elongate or compress by the same amount of displacement. Therefore, we can write as the net force of the displacement of mass m, F equal to minus kpx. Kp is effective spring constant in the directions of parallel. So, F equal to minus of k1x minus of k2x. The equations 10.45 and 10.46 we can modifying both our left hand side will be same, so equating in right hand side. In equations 10.46 we are taking outside of the common negative sign, so we get this equations of minus k1x plus k2x. So equation 10.45 having the negative value, so both are having this negative sign, so cancel to each other, so we get the value of kp equal to k1 plus kx. Because of the common term also hearing of x term, so cancel to each other of this equivalent signs. So generalizing for n spring connected, we can write as summation of I equal to 1 to n into ki. This is the spring connected in the combinations of parallel. So in case of conditions will be applied, we are connecting in n springs. The force constant Kp equal to Nk. This implies that the effective spring constant increases by a factor of n. For the spring in parallel connections, an effective spring constant is greater than the individual spring. You know that very well. Thank you, students. These are the two questions to revise. If you have any doubt, please contact me. Thank you.